In this video, we look at an example of proof by induction. This is a method that we can use to demonstrate or to prove that a mathematical result is true, and it's particularly useful if you've got a high number or even infinitely many cases to demonstrate within your proof. So we're going to look at the example of this finite series. If you're just starting this topic on proof by induction, you'll probably see quite a lot of examples to do with finite series, but the method of proof by induction can be applied to a wide range of types of proof. It doesn't have to just be a series result like we're going to look at. So we're going to work this example in a moment. Before we do that, we're going to chat about the theory of proof by induction, how it works, what the strategy is. But before we do either of those things, let's just think about this example we're going to work in a moment. So it's telling us that we've got the sum from r equals 1 to n of r. If you've done some work with series already, then you'll recognize that this is a very common result, but this is a very simple term here. This term could be a lot more complicated. All that it means is you're going to be putting in the number values between 1 and n and then adding them all up, because remember the sigma tells you to add things up. So just to take an actual concrete example, let's say that we wanted to make our n value 5. So we're taking the sum from r equals 1 to 5 of r. So that just says that you replace the r with these numbers between 1 and 5 and then add them up. So you get 1 plus 2 plus 3 plus 4 plus 5. And then we would just be tasked with adding those up. Now for a small number like 5, that's quite easy to do. I think this comes to 15. And you might wonder, why do we need a general result for that? Because that was quite easy to do. We just listed the numbers, added them up, and then we're done, right? But the challenge is, of course, when this number gets higher, even if it gets to 10, it would start to become quite cumbersome to add the first 10 terms together. 20, 50, 100, 1,000, a million, it's going to be impossible, right, to add those all together. So having this general result becomes a lot more useful. So how does this result work? Well, it says that whatever your n number is, your highest number in your series, you just substitute that number in there and that will give you the sum. In other words, in our case, you would do 1/2 times n, which is 5 for us, times n plus 1, which is 5 plus 1, which is 6. Timesing those together, 1/2 times 6 gives you 3, 3 times 5 does give us 15. So that just kind of demonstrates that, well, at least for this example here, this little rule, this formula, if you like, has worked. We want to show that that formula works in general, regardless of what the n value is, because you can't test it for every case or infinitely many cases for n. So we need to show that in general terms this result is true, and that's where we're going to use our proof by induction. So proof by induction works on a similar principle or a similar analogy to toppling dominoes. If you've got a stack of dominoes lined up and you want to topple them all, you start by just toppling the first domino, and if you've got them all lined up, then you can guarantee that if one domino topples, then all of the dominoes will topple. Proof by induction works in the same way, so we split it into two parts. So this is our inductive proof, or proof by induction, so I'll just call it inductive proof. And the first part of the inductive proof is what we often call the basic step. And in the basic step, that is the equivalent of just knocking over the first domino. So the basic step is normally trivial, and we'll see that when we come to the actual working in a moment. And then the second step we call the inductive step. That's usually quite complicated, to be honest. Sometimes it can be very complicated, but it's certainly always going to be more complicated than the basic step. Usually it's going to involve a fair bit of algebra. And in the inductive step, we basically want to prove that if it's true for one case, like say if the case was 4 here, it's also true for the 5th case. Or in general, that if it's true for the kth case, it's true for the k plus 1th case. So if you take any general term, it's going to be true for the next term. So specifically what we're trying to show here is in the basic step is that the proof is true, the result is true for n equals 1. And in the inductive step, we're trying to show that if it's true for n equals k, so some just n value that we're going to call k, that implies that it's true for n equals k plus 1. So in other words, if you topple one domino, you can be guaranteed, if they're lined up, to topple the next one. The important thing in the inductive step is that you're allowed to assume that it's true for n equals k. So we can assume that this result is true for the kth case, and then we've got to use that to show that that implies that it's true for the k plus 1th case. So that's a strategy of how all inductive proofs work by these two steps. Let's get into the details. So starting with the basic step. So we're literally just trying to show that it's true for the first case. Well, the first case is when n equals 1. So that's going to be the sum from r equals 1 to just 1 of r. That just gives you 1. That's just like what I've done here, but only going to that first case, which clearly just sums up to be 1. Taking a look at the formula says it should be 1/2 times the n value. Remember, our n value is now 1, so it's 1/2 times 1 times n plus 1, which is 2. So looking at that there, you've got 1/2 times 1, which is 1/2, times 2, 1/2 times 2 is 1. So in other words, that does come out to be 1. So the rule here is true. In other words, the left-hand side and the right-hand side match up for the case where n is 1. So the basic step, which like I said earlier, is usually quite trivial, always quite trivial, is proven to be true. So we can move on to the more important and more challenging part, which is the inductive step. So let me just write out what we're trying to do here. So in the inductive step, we're going to assume that the result is true. So we're going to assume true for the kth case. So we're assuming it's true for n equals k. And it is difficult if you're not used to this, seeing stuff like this, right? N, how can n be equal to k? Just imagine it as being one of the cases within the series of numbers, like 3 if you like, or 4, or just one of them, but we're calling it k. So we're assuming it's true for n equals k, and we want to show that that implies that it's true for n equals k plus 1. Specifically, we're going to assume that it's true for n equals k, which means that this result here, the sum from r equals 1 to k of r, is going to equal 1/2, replacing the n with k plus 1. So I've really just mirrored this result here down here and replace the n with a k. That's our assumption. That's what we're assuming to be true, but more importantly, we have to use that result, okay? We've got to use this result in showing that the n equals k plus 1 case is also true. We're going to use this, and then hopefully that will imply that the sum from r equals 1 to not k this time, but k plus 1 of r is going to equal 1/2, and then replacing the k's in here with k plus 1. So we're changing this k to a k plus 1 gives us 1/2 k plus 1. Changing the next one to a k plus 1 would mean the inside of that bracket becomes k plus 1 plus 1, which is k plus 2. So in other words, this here is really what we're trying to prove in the inductive step. So let's just think about how we're going to do that. Well, it really does depend on what type of problem you're working. A common technique in series is to sum up the first so many terms and then tag another term on the end. So what I mean by that is we're trying to prove this here, right? So we're working with the sum from r equals 1 to k plus 1 of r. But you could think of that as being the sum from r equals 1 to k of r, and then just tagging on the last term, because that k plus 1th term is the term after k. So that would be a little bit like performing the sum of the first 5 terms by summing up the first 4 terms, which comes to be 10, and then just tagging on the last term, 5, adding them together and getting 15. That's what this bit here is the equivalent of your first 4 terms. We need to tag on the last term. The last term is just k plus 1. So we can just tag on that final term, k plus 1, which is kind of playing the same role as a 5. We need to turn this into this. If we can do that, then we've proven our result. So this, though, importantly, is the thing that we're allowed to assume. We're allowed to assume that the sum from r equals 1 to k of r is equal to that. So we can just change this guy here to 1/2 k plus 1, and then we're adding on our k plus 1 on the end. Okay, so how you get from this idea of what you're trying to prove to the mechanics of what you are going to actually do really does depend on the problem. They're not always going to be the same. They're not necessarily going to be like my example. If it's to do with series, though, it will be fairly similar to how I've laid this out. How you take that forward is then going to be a little bit of creativity, a bit of algebra. It can be quite difficult to make the next step. We notice here that we've got 2 terms. We've got this term and that term, whereas the result has just got 1 term. It's all multiplied together. So we're going to have to figure out a way to merge our terms together. One way we could achieve that is to look at the common factor with k plus 1. So if we pull that common factor in front, that would give us k plus 1, and then just factorise in to get 1/2 k plus 1, which brings us a little closer now to what we want. Just have a think yourself about how you might even want to pause the video and think, how might I get from this form to this form? There's obviously some kind of algebra, but it's not necessarily obvious. There's a few ways you could approach it, but one way you could do it is within this bracket here. In fact, I'll maybe use a square bracket. You could pull out a 1/2 common factor and then factorise as k plus 2. Importantly, it would have to be a plus 2 in the bracket, because 1/2 times k gives you 1/2 k, 1/2 times 2 gives you 1. So these two lines are equivalent, just written in a different way. Notice now then you've got 1, 2, 3 things multiplying. The order doesn't matter. You can pull the 1/2 in front. So just doing that, we would end up with 1/2 k plus 1 k plus 2, which is the thing that we were trying to prove. So easy, right? Yeah, so sometimes in here it can get a little messy, I'm not going to lie. It just takes a little bit of experience to know what to do with some of these scenarios. But the overall approach, the strategy never changes. So just to quickly recap what we've done there. We've run through the basic step, which was proven it true, for the case where n equals 1. We've now completed the inductive step, which is showing that if it's true for n equals k, and indeed using that result for n equals k, that has to imply that it's true for n equals k plus 1. In other words, we've toppled the first domino here, and we've shown here that if you topple any domino, you automatically topple the next one, which proves that you're then going to, if you start the process, if you topple the first domino, I know I'm using this analogy too much now, but if you topple the first domino, you will therefore topple all of the dominoes. So in other words, this result here is true regardless of the n number. It's true for n equals 1, but that now we've shown to be implying that it's true for n equals 2 and 3 and 4 and 5 and forever, whatever your n value happens to be. So I hope that makes sense. Proof by induction is not easy at first. You've got to learn the overall strategy, and more importantly, practice a range of questions so that you can adapt it to different situations. So I hope that helps. If you've got any questions or comments, just leave them in the box below.